Hi, everybody. Sorry about the delay there. Welcome back to Chem 121. My timing is all off today, and I had to make lunch for myself. Realized that I had no time, so I threw a pizza in the oven. Realized that I had no time for even that, because it took 30 minutes to bake. It just came out of the oven, and I'm sitting in the kitchen taking a bite of pizza while class is starting, going, it's too hot! And then quickly swallowing it, and then taking another bite, and it's too hot! Because that's just something that I do, is I eat food way too quickly when it comes out of the oven. This is not a tablet. This is a piece of paper for Dungeons & Dragons that I don't need on my desktop right now. So give me a second to fix all this, and then we'll get started. The other delay that I had today was that I was originally going to use the soundtrack for Fallout, and then I realized, that's probably a little too on the nose for everything that's going on in the world, and I just don't want. I can't even. So we're not doing that. So I've chosen Metroid Prime because that's also a quality soundtrack that is kind of ambient and also maybe a little foreboding for the last 2 weeks of class. Can you believe that we're in the last 2 weeks of class? What the hell, right? Like, normally I feel like the winter quarter kind of goes by not super slow, but it takes a while to get there. This has flown by. I can't believe how quickly we've almost reached the end here. And we only have like 4 lectures left, maybe 5 if we go again on Wednesday. And then a review session next week, and then you have midterm 2, and then a final, and then it's over. That's it. We're done here, right? Uranium fever? Oh, goodness. All right, what are we going to do today? We're going to talk about dilutions, which are just a a procedure that you're going to follow to turn one solution concentration into another. And the way that you're going to do that, practically speaking, is through the addition of water. So if I have something that is concentrated and I put water in it, it gets less concentrated. You've probably done this sort of thing with, like, say, beverages. So real common, if you buy, like, frozen, like, orange juice or whatever, and it says on the container concentrate, what you do is you put that in a container and then you add water to it. You add like 4.5 of the cans that it came in of water, and then you stir the heck out of it, and then it tastes appropriate. But if you drink it as is, well, one, it's a frozen slush, so you have to let it melt. But two, way too sweet. Like, you don't want to do that. This is popular if you have kids. Kids love frozen orange juice, and diluting it from concentrate is very effective. Because really all that they are selling you is the orange juice without the water. And water is fairly abundant, and you can provide it on your own. So we're going to do that from the perspective of the laboratory, where I don't want to ship you, say, IV bags that are already prepared, because that's a lot of water we would be shipping around, right? So instead, what we are going to do is we're going to ship you the concentrate, and then you can add the water yourself. So that's what we're going to do here. I also just realized that I didn't note what's at the bottom. So tomorrow, Tuesday, the 1st of March. March? Really? Like, crazy. Quiz number 7 and lab worksheet number 4 are due. Remember that the deadline is 24 hours later, so if you need more time, it closes on Wednesday, so that's when you'll do it. I did also return your lab worksheet number 3s, unless you turned it in late for any reason, such as NQA, or I couldn't open your file and asked you to send me a new copy, or whatever. I will work on those today. I just didn't have any time yesterday. I've been playing a little bit too much Final Fantasy VI. We'll just come straight out and say that. Okay. So we've already talked about what the process of dilution is from a perspective of, like, what are we generally doing? We're just going to add water. Now, pragmatically speaking, if you are using a solution where the solvent isn't water, you would just add more of the solvent. So you can dilute a solution by using whatever the appropriate solvent is for the task, and then adding more of it. The reason that this works is, so if concentration is represented by, say, molarity, and the formula for molarity is this, then if I increase the volume by adding water, then this number gets bigger, right? So let's say I had 1 liter of solution, and then I added an extra liter of water. Then instead of dividing by 1 liter, I'd be dividing by 2 liters, because the total volume at the end, assuming the volumes add, which they don't, but if you're just adding water to itself, generally you are safe doing that. That would be a 2-liter solution now, and thus we would instead be dividing this number by whatever number of moles there are divided by 2 instead. So as this number increases and this number on the top remains the same, the result is that the concentration goes down, because you're dividing by a bigger number. Something divided by 1 is going to be larger than something divided by 2, which is going to be larger than something divided by 4, and so on and so forth. So as we keep adding water to the solution, things get more and more dilute. I don't know if you can hear him, but Kresnik is crying it, the song of his people in the background. Kresnik, what do you want, bud? He immediately stopped as soon as I said his name. All right. Your textbook has a formula for dilution, and it is this. This looks a little bit like alphabet soup, but in reality, it's not too bad. What does L mean in the formula? Oh, back here? So that is liters of solution, or volume. And so that was the formula for molarity. All right, here's our formula for dilution. The S side of the equation is the stock side. The stock solution is what you start with. It's in the stock room. You stock the stock solution in like a cupboard or a pantry or a bin or something like that. And you have it handy for later use. The D side is the dilute side. This is what you prepare. So after you have done the active dilution, you end up with the dilute solution. This is the end result of your work. Now, the rest here, C is a concentration. And the units are going to vary depending on what your concentration is in. If your units are molarity, then you're going to put in your concentration in terms of molarity. If it's percent by mass, you're going to put in percent units by mass, and so on. Remember that you want all the units. So for example, if you were doing this in like a percent mass here, then your units for that would be whatever your number is, percent mm, or WW or whatever. Or your units could just be moles per liter. Or your units could be percent m/v, or so on and so forth. So these are all possible units that can go into the concentration spot. Now, as long as you use the same units on both sides, then they'll just cancel out whenever you do the work here. So as long as these two have the same units, you're okay. Same thing with volume. The volume terms have to have the same units as well, and then V is just volume. So we'll write that down. That's a very wide M. I apologize for bonking the pen against the tablet, I guess we'll say. So what this says is that if I take the concentration of the stock solution and then I take some volume of it, the product of those two things is going to be the concentration of the dilute solution times its volume. And what I'm going to do is I'm going to clear the screen and show you why this works. So let's suppose that we're working in moles per liter. So the concentration of the unit on the stock solution side would be moles over liters. And then the volume of the solution we would measure in liters. And then this happens when I multiply those two together. In other words, the product on that side is just going to be equal to the number of moles of solute that I have. And the same would be true over here. And so what you end up having is just that moles equals moles is your result, right? Now that makes sense, because if this is our flask for our solution here, and I have this many moles of solute in my solution, where the solute is the blue dots or whatever, and then I dilute it by adding water, not only does the flask get bigger, but I have the same number of moles of solute. So from the calculations perspective, that checks out, right? However many moles I use to prepare the stock solution is going to be equal to the number of moles that I have of the dilute solution at the end of the day. Because all I'm adding to the solution is just water. I'm not adding any moles of solute. I'm only adding solvents, right? Now, conceptually, that should still hold regardless of whatever the units are. So if my concentration is expressed in some other unit, such as mass percent or volume percent or whatever, it should still work. It's just that the units work out really nicely here. Hi. Say hi. Hello. Do you want to say hi to the class? Sorry, my cat is right here yowling in my ear, and I'm trying to, like, appease him so he'll go away. So I'm just going to sit here and pet him. All right. So there is a more detailed explanation. There he goes. He just left. Of what the variables mean. So CS is the stock concentration. VS is the amount of stock solution that is needed in terms of volume. CD is the dilute concentration that you want to make. And then VD is the new diluted volume total that you're going to prepare. Now, generally speaking, you're going to be solving for this one. This is not universally true, but for your purposes, this will be the most useful variable by far. And the reason that that one is going to be what we solve for is because this is known. Because it's printed on the bottle in the stockroom. If I am the manufacturer of IV saline solution and I send you 30% saline solution, you don't have any say in that because you just bought it from us. And so you would say, okay, well, the stock solution is 30%. I want 0.9 to administer to patients. What would I calculate? Now, down here, the diluted concentration, generally speaking, you choose this, since you are preparing the solution that you want to. So you would select what concentration you want. In this case, for an IV bag, you would want 0.9%, because that is isotonic with blood cells. And so that would rehydrate a dehydrated person without causing overhydration, which would cause their blood cells to rupture. And that would be all sorts of bad. And then the volume of the diluted concentration that you make, you get to choose that too. Do you want 1 liter or do you want 100 liters? How many patients do you have today? How many do you expect? Are you trying to prepare ahead of time? You can select this term too. The math will automatically work itself out based on those two things you make, or you chose. Because, remember, this number times this number is just moles, right? And so you are essentially choosing the number of moles of solute that you need. And I've already told you how concentrated it is, so we're just going to solve for this one. All right, so let's do an example, and we'll show this in action. So I want to make 100 milliliters of 0.0500 molar HCl. But all I have is 4 molar HCl, and that's way too concentrated. That will destroy whatever substance I'm working with. I need something way more dilute. How do I prepare the solution? Okay, so just like when we were doing gas laws, I like to write down the formula first. And then I do this sort of thing. We're going to make a little chart. And then in the chart, we're going to fill in the numbers. So this intersection would be CS, this would be CD, and so on and so forth. Oops. Went back too many steps in the history tool. Okay. So according to the problem, I need 100 milliliters of 0.0500 molar HCl, but I only have 4 molar HCl. You'll notice that I've sort of scrambled the numbers up here. Normally, I would say the before thing first. But in this case, the context of the problem makes sense to say what you want, and then here's what you have. That is a normal thing that we are used to. Here's what I want out of this, but here, from these things, do it. So we have to use our understanding of how the problem is worded to organize this information. The first hint that I can give you is that the concentrated solution or the stock solution is always going to be the bigger molarity. So my molarities are 4 moles per liter and 0.05 moles per liter. 4 is way bigger, so that's going to be this one. So the stock solution is 4 moles per liter. The dilute one is going to be the other number. And then I just have to place where the volume goes. So I need 100 milliliters of this one. Therefore, I would place it there, and then I'm going to solve for V sub S here. So if this is the variable that I'm solving for, I'm going to do something like this. I'll divide both sides by the CS, and now I can just plug in the numbers, right? So concentration of dilute was 0.0500 moles per liter. The volume of dilute was 100 milliliters. Do we need to turn that into liters? You can, but bear with me. We'll just see what happens. And then finally, the concentration of stock solution was 4 moles per liter. What units cancel out? Well, molarity and molarity cancel out, right? And that's going to leave us with just whatever's left over. And that's going to be the units of our answer. So whatever unit you put in is going to be the unit you get out with respect to volume. So if you entered a number in for volume of the dilute solution in liters, your answer would be output in liters. If you put it in gallons, it would come out as gallons. So it's whatever you put in is what you get out. So you can use any unit you want to. I would recommend using the unit that the problem asks you to, if it is convenient to do so, of course. So like if I give you milliliters and I ask you to give me the volume in milliliters that you need for the stock solution, then just use milliliters, right? No reason to do extra work if you don't have to. So we'll punch all these numbers in. And the number I get is 1.25 is my answer. Now, contextually speaking, what does this number mean? We've solved for a number, but how do we use it? Does this answer the question that's being asked? Well, at the top it says, describe how to dilute the solution. If you told me that you've prepared the solution and you handed me a piece of paper that just said this number on it, I would say, this isn't a solution. This is an answer to a problem, but it is not the solution that I need to administer to the patient or whatever. So what do I do with this number? So remember that Vs is the volume of the stock solution. And so we need to put that in a container that holds the volume that we want to prepare, and then add the remainder of this as water. So here's how you make this dilution. So step 1, we're going to add the volume of stock solution that we calculated of, and we're going to add the stock concentration here, which we're going to write as 4 moles per liter HCl, which is this. Where are we going to put this? Are we going to put it in the trash? Are we going to put it in the toilet, the ocean, a shot glass? No, we're going to put it in a flask for preparing the solution, right? So add whatever volume you calculated of 4 molar HCl to A, and according to the problem, we wanted 100 milliliters of this. 100 milliliter volumetric flask. So the word volumetric just means, hey, we're going to determine the volume very precisely. So we're not just going to use like a measuring copper container or whatever that just has lines on it. This number right here is the volume of the dilute solution that you elected to prepare. As a result, sorry, I'm coughing. I just don't want to cough on the mic. As a result of you choosing the volume to prepare, that number is going to depend on what the problem is asking you or what you want it to be. So that's step number 1. Visually, that's going to look like this. Here's my flask. And there's a mark on it that says 100 milliliters. I'm going to take my 4 molar HCl, and I'm going to add 1.25 milliliters of that, because this is what we calculated, right? All right, and so there it is. It's right there at the bottom of my flask. You probably shouldn't keep your HCl in a squirt bottle, but that's okay. All right, that was step 1. Step 2 is we're going to add all the remainder of the volume as water to the fill mark. So we're going to add now H2O until we reach this line. My pen kind of goofed out there. Step number 3 is that once you have prepared the solution, put a cap or seal it in some way, and then invert it so that you can mix it well. Do this for roughly 60 seconds. That's about the amount of time that you need in order for the solution to be well mixed and homogeneous. Takes 60 seconds of mix. And then there is a secret 4th step, which this is optional. Enjoy. All right. So that's how you make a solution. Whatever number you've calculated in your procedure is going to go right here. This is how much of the concentrate you add. Then you're going to add the remainder of the solution as water, and then stir it really good and enjoy. Consume only if instructed to. If it's orange juice, absolutely, down the hatch. Hydrochloric acid, not a good plan. Don't do it. All right, that's how you do dilutions. So I'm going to give you a dilution now to do. For you to calculate the amount of stock solution. So here we go. I'm going to give you 4 molar HCl again, because it's just what I have in the stock room. We're not very creative. We only have 1 solution in there. I want you to make these 3 solutions. So you're going to use the dilution formula 3 separate times. So these are independent problems. So I want you to calculate how much stock solution you need to make 25 mils of 1 molar HCl. And then write out the procedure. Step 1, what did I add to what container? How big was the container? Step 2, what did I do with the water? Step 3, shake it all about, that sort of thing. Hokey pokey. Hokey pokey the solutions here. So describe these as best you can in the chat for number 1, 2, and 3. And in about 5 or 6 minutes, we'll go over the solution to the solution. All right, let's do 1 or 2 more minutes to do any of these solutions. Once you have an answer, go ahead and post it in the chat here, and then Maya will approve it because she just jumped up here. Say hi. Say hi. Hi, Maya. Hello. Maya. Maya says hello. And let's go over the answers. Oh, I said 1 or 2 more minutes. I'll give you 1 more minute. Sorry. All right. Let's go over the solutions here. All right. So our diagram that we have here on the screen, this is a universal blueprint for making solutions. So we can use this to prepare any solution that we want to. So all of our procedures are going to be written out the same way. We just need to write all of this based on information from the problem above. So I need this molarity, this concentration, etc. So let's create a little template here. And then we're going to solve in each of these cases for this. All right. I'm going to hit a button here real quick. There we go. All right, so for the first problem, every time I'm using 4 molar HCl, so I'm going to just put this here. And then I want to make 1 molar HCl. And I want 25 milliliters of it. So when I go and enter those numbers in, I would get, so the concentration of dilute is 1 molar. The volume of dilute is 25 milliliters. And then the concentration of stock is 4 molar. And the molarities cancel out. And I believe you should get this when you are finished with the calculation, but I'm doing that in my head, so let's just do this. Yeah, that's what you get. Okay, so now that we have that volume, I'm going to click on that thing here. Let's go do our 4-step plan here. So step 1 is to measure how much volume we had. So I'm going to write it like this. Into a whatever volume we want, volumetric flask. And there you go. So those are the 4 steps. So let's just go fill in the information here. So I had 6.25 milliliters that I measured out. So we're going to do 6.2. I didn't put enough space here. 6.25 milliliters of 4.0 molar HCl into well, how big did I want it? I wanted 25 milliliters volumetric flask. So there would be your procedure. I'm going to take 6.25 milliliters of the stock solution, pour that in a 25 ml flask, add enough H2O to hit that mark, mix it well, and enjoy. All right, so there's the whole calculation and everything all on one screen. There we go. Now, why did I bother to do that? Because now for the second problem, look what I can do. Boop. Oh, that didn't work. Hold on. Boop. There we go. So we can just do it again for problem 2, right? So let's do that. So problem 2, I want to make, I still have 4 molar HCl. This time I want to make 2 molar HCl. And I want 250 milliliters of that. So I'd solve for the same thing. I just realized that for the previous problem I didn't do sig figs. It should round to 6.3. So let's do the calculations same way. So 2 moles per liter. The volume of dilute would be 250. And the stock concentration would be 4. So this would be 125, but I only get 2 sig figs, so it'd be 130 milliliters. And so we'll just put that in here. So measure 130 milliliters of 4.0 molar HCl. I could do a better CL. There we go. Into a 250 milliliter volumetric flask. There you go. So you can now easily prepare concentrations of all these things, provided that they are well-defined. Well-defined meaning that you sit down and decide what they are ahead of time. All right, let's erase that and let's do it again. So for number 3, we have 1,000 milliliters we want this time. I'm still using the same 4 molar stock solution, and this time I want 0.0250 moles per liter. So let's run it through the calculation again. That's the wrong number. So concentration dilute, sorry, 0.0250. Volume dilute is 1,000 here. And then concentration of stock is 4. And those disappear. And this one I have to actually punch in the calculator for sure. Oh, it's 6.25 again. Look at that. I only get 2 sig figs, though, so this time we'll actually write the correct number of sig figs. That should be a dot, which didn't really show up there very well. There we go. Measure 6.3 milliliters of 4 molar HCl into a 1,000 milliliter volumetric flask. And that will be our solution. And you are all set. All right. So, when in doubt, follow this blueprint, the steps 1 through 4, to prepare your solutions. And that's all there is to dilutions. Now, if you have a different unit, for example, you don't have molarity, you have, like, say, percent by mass or percent by volume or whatever, The rules are exactly the same. You just, instead of writing M, you would write %mm or whatever. But you totally just operate the numbers in the same fashion. All right. When we get back from the break, what we're going to do is we're going to talk about colligative properties in osmosis, which are two features of solutions that occur when you add things like salts to them. This is particularly relevant up here in the winter because these have impacts on stuff like freezing point and boiling point. We're going to talk about that, but because there's only like 3 minutes before the break, I'm going to just go straight to the break. And when we come back, we'll do more of this. So I'll see you in just a little bit. Hi, everybody. Welcome back. I swear that 10 minutes went, like, by super quickly. Like, I'm in, like, a time loop or something where everything is... Not time loop, I guess, but... Time vacuum? I don't know. Everything's going so fast today. Alright, let's continue. If I could find my pen. There we go. Alright. This next section, colligative properties, involves some characteristics of solutions that we can somewhat control. Now, a colligative property, which, in other words, one of these four things that we're going to talk about here, is a physical type of property that only depends on what amount of solute is in the solution. The identity of the solute, like its chemical identity, is irrelevant. So we're not really doing chemistry in this section. This is just physics. That being said, it does have chemical consequences that are relevant in biochem. So we're going to see that when we talk about osmosis in a second here. I'm clicked on the wrong thing. There we go. All right. Now, the more solute you put into your solution, i.e. the more concentrated it is, the stronger these effects will be. And these effects are all listed at the bottom here. The 4 effects that we're going to consider are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. In other words, if I have a higher concentration, these effects are exaggerated. So the vapor pressure would be even lower, or the boiling point would be even higher, or the freezing point would be even lower, and so on. All right. Now, the type of solute that you are looking at is going to, in fact, dictate the effect of these colligative properties based on how many particles are present. For example, if I have glucose, glucose is not an ionic compound. Glucose is molecular. What that means is that this molecule, C6H12O6, remains as one giant chunk, and it floats around the solution as such, and it contributes 1 particle per molecule. But if I had NaCl instead, NaCl is ionic, and it will dissociate into 2 pieces. Because all the solutions we're talking about are water, right? In water, ionic compounds, provided that they're soluble, will dissociate. This will give us 2 pieces. And what that means is that if I put in 1 particle of NaCl, 1 formula unit, for example, at the end of the day, I get 2 pieces of worth of effect. As opposed to glucose, where I only get 1 piece worth of effect. So, things that dissociate into more pieces, more ions, or more particles, will have a stronger effect on the solution and the colligative properties that we're examining. So, your textbook may refer to this as the Van 't Hoff factor, or the dissociation factor. Alright, so looking at these, which would have a stronger impact on colligative properties, CO2 or KBr? I've given you a hint. Type in your guess in the chat, and we'll go over the answer in about a minute. Alright, looks like we have 2 different answers here. Which one splits into more properties? Well, molecular compounds only split into 1, or they don't split at all, so they would just contribute 1 particle. But KBr would contribute 2. So KBr should contribute more to colligative properties. How about these 2? Which one's more effective? They're both ionic. Assume that they are soluble in the solution we're looking at. Which one will have the stronger effect? Calcium chloride or sodium phosphate? All right, so how many particles will each of these pieces split into? So calcium chloride would split into a calcium and 2 chlorides, whereas sodium phosphate would split into a bunch of sodiums and a phosphate. Which one has more pieces? This one gives you 3. This one gives you 4. So the one that splits into more pieces should give you a stronger impact. All right. Let's talk about these effects in more detail. So the first one is vapor pressure lowering. The gist here is that when you add a non-volatile solute to the solvent, what I mean by non-volatile is that the solute that we're adding does not evaporate. So for instance, something like sodium chloride, NaCl. NaCl does not evaporate. It's a solid at room temp, right? The vapor pressure goes down. And the reason for this is because if we look at the surface here, when things evaporate, they can only do so by leaving from the surface. If the surface is entirely solvent, every position on the surface layer is available for a molecule to potentially leave and enter the vapor phase. But if a solute is there, those positions are blocked. Since the solute does not evaporate, and water cannot share that space with the solute, the water cannot evaporate as easily. Part of the surface is blocked away. And so the amount of evaporation that occurs is reduced. So when you add solute, vapor pressure goes down proportionately. In fact, it's a direct proportion. If we were going to actually do math with this, the vapor pressure lowering would just be whatever percentage of the surface is solvent. So if I had 20% sugar and 80% water, the vapor pressure would be 20% lower because 20% of the surface is obstructed. Now, because vapor pressure and boiling point are tied together, if I reduce the vapor pressure of something, I make it harder to boil. And as a result of that, I have to heat the solution further to get the vapor pressure to equal the atmospheric pressure and thus cause boiling. So, the boiling point of a solution with a solute in it goes up. Now, an example of this would be something like antifreeze. So if you put antifreeze in your automobile, in the radiator, your engine has a tank with water and antifreeze in it. And the water's purpose is really just to absorb heat from the engine so the engine doesn't overheat and then melt. Now, if the water absorbs too much heat, the solution boils and all the water goes away, and then your engine will overheat, and then you have to stop the car 1 hour up the mountain and then sit in the scathing heat while the people who have the 70-year-old truck that they've brought for the 30th year in a row to the campsite have to fill the radiator with water again, only for this to happen again in 20 more minutes when the car overheats again, because they didn't buy any fucking antifreeze. Did this happen to me as a child? Maybe. We used to go camping all the time, every year, with another family, and the other family had this really old truck, and every year, without fail, it would overheat as we drove up the mountain. And we'd have to sit and wait for the engine to cool off And then we drive like 30 more minutes up higher elevation. Had to sit and wait for the engine to cool off. It was super frustrating as a kid because it's so hot in the car. So, yeah, put antifreeze in your car because what will happen is the water's boiling point will go up, and then your engine can put more heat in that water and be less likely to overheat. Yeah, if it's oddly specific, it's for a reason, right? Now, we're going to come back to the antifreeze example when we talk about freezing point depression, because the flip side of this is when you have water in your engine, you obviously don't want the engine block to freeze, because then it expands and damages your engine, right? Because ice is less dense than water, and so water expands when freezing. This is why things like your water, like the water main out here broke the other day at my apartment complex because of the freezing temperatures. I woke up and tried to use the water, and nothing happened. And what? Why is the water shut off? Oh, there's a public works notice on my door. Yeah, the water main's broken. We're on it. Thanks, City of Everett. I had water back like within 2 hours, so it was great. Another example, though, of boiling point elevation that I can think of is if you add salt to, say, pasta water, it actually needs, if you add lots of salt to it, not only does it make your pasta taste good, but the boiling temperature goes up very slightly to, like, say, 101 Celsius or something like that. And then you cook your pasta slightly faster. Freezing point depression operates in sort of the same way that vapor pressure lowering does, too. Solute particles block the surface of our liquid to prevent evaporation. In the same manner, solute particles, which are these little orange guys here, can block the ability for something to freeze. Freezing requires us to create a solid structure. A solid structure requires our molecules to be lined up very, very specifically so that their intermolecular forces take over and lock things in place. If you have a solute in the way, that interrupts these interactions and thus lowers the freezing point. Now, because freezing point is really just what is the maximum speed that molecules can move before they just get attracted to something and lock into place. If I have stuff in the way, I have to slow down my molecules even further before they will arrange into a solid. Now, a practical consequence of this is in your antifreeze in your radiator, of course. You don't want your engine block to freeze, so if we put antifreeze in the water in your engine block, then the water cannot line up with other water molecules to freeze into place, and thus your engine block's solution remains in the liquid state and not frozen and expanding and possibly cracking your engine block. Another practical example of this is applying salt to the road. This is very, very useful in the winter. Freezing water on the roadway creates a lack of friction, and that is very difficult for vehicles to deal with, particularly because they are very heavy, and heavy objects sliding around uncontrollably is generally a recipe for very bad, right? I don't know if you've ever had a vehicle skid out of control while driving. I have, and it is no fun for anybody involved, especially the curb that you run into sometimes. I used to only have a Harley Davidson Sportster, and I would have to drive even in the winter, and ice was the thing that terrified me the most. And yet, ironically, because my motorcycle was light and I was going very slow, and I had two wheels of traction all the time, two wheels, I should say. I did pretty well. I never dropped my motorcycle on ice, and I drove on ice probably like 3 or 4 times, I would say, when I absolutely had to. The pickup truck that my friend lent me one year, though, however, was very, very unwieldy because it was rear-wheel drive, and there was no weight in the back, and so nothing happened when I was on ice. I basically would skid out immediately. So ice on the road is really, really bad for driving and maintaining our way of life. So are pandemics, but, you know. So what we do is we add salt, sodium chloride, to the road. The more sodium chloride is sprayed on the ice, the lower its freezing point goes. And as long as we can get that freezing point to go below the current temperature, the ice will melt, and then we will be able to use the road as intended. So this is something that we do. We spray the roadways with a sodium chloride solution, and then the ice thaws out because its freezing point, instead of being 32 Fahrenheit or 0 Celsius, becomes like 16 Fahrenheit or negative 10 Celsius or something like that. And this is a very common thing. Now, this only works with particles that dissociate. You may remember a few years ago that the mayor of Seattle decided, hey, we're not going to use salt. That's environmentally unfriendly, despite living next to the ocean. We're going to use sand instead. Well, sand does not dissociate. Sand is just one contiguous particle, right? Sand is silicon dioxide for what it's worth, but it's insoluble. So it doesn't break into ions and thus has very limited impact on lowering the freezing point. It's generally just meant to increase traction, but it doesn't do a great job of that. And so that entire year, everybody was just like freaking out with the mayor, like, why did you use sand instead of salt? And like the mayor immediately went back on this decision like a week later, and the salt came back out, and everything was back to normal. Okay, so those are our colligative properties that we're going to talk about in a very brief level of detail. Osmotic pressure in the next section, we're going to talk about in more detail. All right, so what is osmosis? You're actually studying that this week in the lab experiment. Osmosis is the movement of a liquid solvent through a barrier that is known as semi-permeable. So this membrane right here is semi-permeable because some things are allowed to go through, but other things are not. That's what semi-permeable means. Permeable means something can go through it. Semi-permeable means we have limited permeability. Only certain objects are allowed. Generally speaking, this is restricted by size. The holes are just only so big for particles to slip through. However, you can also make something semi-permeable with regards to, say, charge. So ions could or could not flow through a membrane, whereas something that was neutral could. Cell membranes are like this. Water can generally flow through certain channels in the cell membrane, but ions can't because it's semi-permeable for specific substances. Now, when water moves through a semi-permeable membrane, and ions cannot, this results in a concentration change. And so what we need to do is draw a picture of this. So this process is called osmosis. And there's going to be a picture on the other slide, but I feel like if I draw out the picture and you see my drawing in action, that this helps a little bit. So we're going to go clear, and then clear. And then I'll get rid of this layer. All right, so what I'm going to draw is I'm going to draw just a generic cell that has been split in the middle by a semi-permeable membrane. Permeable. There we go. So this barrier is semi-permeable. And so what this means is that water, which I'm going to illustrate in blue, can move back and forth through the membrane. However, the ions that are inside, which I'm going to illustrate in black here, because that's the other color I have, cannot. All right. Now, all solutions will attempt to mix natively. And what this means is that solute and solvent particles will shuffle about in random directions until they are homogeneous. So when you let things mix together, like say adding food coloring to water, eventually over time you will have a homogeneous solution. It will attain homogeneity. Now the semi-permeable membrane in the way prohibits this somewhat. This is generally a good thing. We don't want our body to be homogeneous, right? Like if your blood was homogeneous, then all the cells would rupture and dissolve. That would be bad. Your blood could not carry oxygen as effectively. So semi-impermeable membranes have a purpose. And a consequence of this is that if ions can't move through, they just kind of bounce off here. My solution still wants to mix so that it will eventually be homogeneous. However, the only way that it can do that is for water to be the substance doing the motion. And so what water will tend to do in this case is it will say, okay, how do I get the molarity on this side? How do I get this statement to be true? All right. On the left side, I have a solution that is higher in concentration. And on the right side, I have a solution that is lower. And I need these to equalize. So, mathematically speaking, these numbers are fixed. Because I cannot move ions left to right. I'm going to have the same number of moles on both sides of the membrane. All I can do is make the volume change by moving water from one side to the other. So which direction will the water go? Well, if I have the higher concentration on the left and I want it to be reduced, then I need to increase its volume. And if I have the lower concentration on the right and I want its volume to increase, I need to reduce that volume, right? So if I do this, if I move water in this direction, from the lower concentrated side to the higher concentrated side, then the volume on the lower concentrated side would reduce and its concentration would go up. And the volume on the right side would increase and cause its concentration to go down. These would then eventually reach equilibrium, and I would have the same concentration on both sides. So, because water and solutions want to do this mixing thing, this is the observation that we observe. And this is called osmosis. Osmosis is the flow of solvent, in this case water, and it will move from the low concentration solute side to the high concentration solute side. And the intent is that it is going to try and equalize them. So osmosis is just water moving from the side that is less concentrated to the side that is more, because in doing so, it will mix the solutions such that, even though the barrier is in the way, they'll have the same concentration throughout. Now, anywhere that there is water and ions, this happens. And so, all the time, your body is exchanging water into and out of cells. Now, if you eat a lot of salt, then you increase the concentration of ions in your bloodstream, because the salt goes into your bloodstream. It's absorbed in the intestines and stuff like that, right? Then your body will produce an effect, a physiological effect. And the effect is you get thirsty, right? Why do you get thirsty after eating salty food? And the answer is, well, because you're losing water from your cells from all the salt that you ate. And so now your body gives you this effect that you recognize as, oh, I need to drink more water. I'm thirsty. This is also why excessive thirst is a very common symptom of diabetes. If you're diabetic and you don't know it, one of the most common warning signs is that, well, one is you become comatose. That's obviously very bad, but the most obvious symptom that you can observe is that no matter how much water you drink, you're still thirsty, even though you have to pee constantly. And the reason for that is because you have glucose in your bloodstream that isn't being removed by insulin or whatever, and your kidneys are just working like crazy trying to filter it out. So the other thing that you can test for is there glucose in your urine? Because that's not something that's supposed to happen. But if you have too much of it and it saturates your bloodstream, you feel the sensation of thirst. And so this is all consequences of osmosis. Here's a different picture of this. You can see that over here on the left, I have my semi-permeable membrane right here in the middle. And I have a solution that's more concentrated and a solution that's more dilute. The water is going to move in this direction to make the solutions have the same concentration. So there will be less water on the right and more water on the left when we're done. And you can see that the intensity of the color is reduced on the left and is enhanced on the right. Very slightly. It's very subtle. Now, if I do this in a tube of water like this, the water level will actually increase like this and reduce like that. And I get this pressure differential. And this, because this tube has a mass and is pushing down, and this, the force of osmosis is pushing against it, that is where the term osmotic pressure comes from. Now, this pressure is felt by everything around it. So the water moving out of your cells or into your cells exerts a pressure on the cells. This is partially where blood pressure comes from. Blood pressure is more or less a measure of your cell's osmotic pressure. If you have high blood pressure, then that can be because water is being pushed out of your cells. It's being squeezed out, more or less. You're putting a higher pressure on the cells and forcing water out of them. All right. Now, all cells are made of membranes. Cell walls are just a different type of membrane. Okay. Let me retract that statement. So your cells, whether if you're animal cells have cell membranes, or plant cells which have cell walls, are all subject to external forces. And if that pressure that is pressing inward on them is too high or too low, something will happen to the cell. There is an ideal equilibrium where it's just right in the middle. But if you hydrate something too much or dehydrate it too much, the pressure on the cell wall or cell membrane can cause a rupture. And that's obviously very, very bad. Now, the way that we control this feature from happening is by controlling the amount of solute. So if I have more or less solute in my solution, the osmotic pressure will be higher or lower. And we get a different result depending on which case we're looking at. We're going to talk about that in a second here. Oh, shoot, hold on. You can't see anything here because I'm not on the right slide there. There we go. Sorry about that. All right. To determine osmotic pressure, we have this value called osmolarity that we can apply to solutions. If two solutions have the same osmolarity, they will have the same osmotic pressure. And the way that we do this is we multiply the solution's molarity in moles per liter by this factor. It's called I. I is the number of particles the solute dissociates into. So for example, NaCl, I would be equal to 2. For sodium phosphate, I would be equal to 4, like we determined earlier. And then for CO2, I would be equal to 1. And so on and so forth. This is relevant to you if you were trying to prepare a saline solution, and for example, maybe you didn't have sodium chloride. You had to use something else that was non-toxic, but dissociated into more particles, and you had to calculate it yourself. You can actually do that using osmolarity. And so we're going to do an example of calculation with osmolarity here. What would the osmolarity of 1.5 molar NaCl be? Well, this is just 1.50 moles per liter times I. What would I be for sodium chloride? Well, again, if it splits into two pieces, I would be 2. And the unit that we use is osmol, OSMOL. So if I wanted a solution that had the same osmotic pressure as 1.50 molar NaCl, but I had a different I value for it, so maybe say like glucose. I want to make a sugar solution. I would need a sugar solution that would satisfy 3 osmolarity. Sorry. So in other words, if I was using a glucose solution, and I is 1 for glucose, and I wanted a 3 osmol solution, then I'd have to make a 3 molar glucose solution. That would have the same osmotic pressure as a 1.50 molar sodium chloride solution. So that's where osmolarity comes in. We're not going to really do much with it in this class, but the purpose is just for you to see this sort of calculation and understand that. This will be relevant to you if you ever have to do the math work for preparing solutions, because there are multiple solutions for hydration. If somebody is just dehydrated, you give them saline. If they are malnourished because they have not been eating for whatever reason, then you give them a glucose solution. And you want the molarities to be appropriate because you don't want to accidentally give somebody glucose and then dehydrate them further and then they get sick. All right. What are the consequences of osmosis if the osmotic pressure is handled inappropriately? The first situation occurs if you have a very high solute concentration outside the cell. Inside the cell are ions. I don't know why that line did that. Inside the cell are ions. But if there are not as many ions per unit volume as there are outside, water is going to say, oh, hey, it's too concentrated out there. I want to make everything homogeneous. And so all the water will then come out of the cell. Oh, for fuck's sake. This effect is called crenation. Crenation occurs when you have too much solute in your bloodstream. And so all your blood cells would shrivel up. This is obviously very bad. A shriveled blood cell is unable to transport oxygen effectively, and thus would be a poor unit to do so, I guess. A solution that has a lot of solute in it is called hypertonic. Hyper meaning too much. When your child is hyper, they have too much energy, right? Same principle here. Hypertonic means too much salt in my solution. So hypertonic and crenation, those two go together. The opposite effect happens if you have too little solute out here. So if there's too little outside and you have tons of ions inside relative to that, then what water does is water says, oh, the concentration is too high. I'm going to move into the cell. And so all the water comes in here. So this solution on the outside would be hypotonic. Hypo meaning too little. You've probably heard the term hypo with regards to, like, say, diabetes. So somebody who's hypoglycemic, their blood sugar is too low. Now, if too much water goes into a cell, then the term that's used for this is called hemolysis. Lysis being the rupturing of the cell, and hemo being blood. So, specifically when blood cells do this, this is hemolysis. Maybe it's called hemolysis. I don't actually know how it's pronounced. I just see the word on the screen. So, both of these are obviously very bad. You do not want your cells to rupture, nor do you want them to shrivel up. So, by the Goldilocks principle, there is something in the middle that is just right. And this is where the isotonic solution comes into play. A solution is isotonic if it has the same concentration of ions inside the cell as the solution does itself. What are the isotonic solutions? That's saline solution. Saline solution is specifically prepared so that it is isotonic with human blood. The correct concentration is 0.9% mole mass volume. Sodium chloride. Or in other words, to prepare the solution, you would add 0.9 grams of sodium chloride to enough water to prepare 100 milliliters of solution. Then when you times this by 100%, the hundreds just cancel out, and you get 0.9% MV. Yeah, you can cancel out numbers. Numbers cancel too. 100 divided by 100 is 1, right? So that is the solution for saline solution. So 0.9 grams of sodium chloride per 100 milliliters, or 9 grams per liter. So if you are making saline solution, remember that one for your nursing program course, because when you get there, that number is going to be handy. 9 grams per liter. That's what you got to know. This is for people who are dehydrated. If you need to administer a solution to somebody who's dehydrated and malnourished, we apply glucose. Glucose is a 5% solution to be isotonic. Why is it so much more? And the reason is because in terms of molarity, glucose is much heavier than table salt is. So to get the same number of moles, we have a much higher mass. So mass volume, our mass volume percentage would be bigger. And so for this would be 50 grams per liter for glucose. Now, your body is not super sensitive to this. So if I am only off by a little tiny bit, you're going to be okay. But let's suppose that I was trying to do analysis of solutions with these preps here. I'm going to put blood in a 1.5 MV solution. So here's my blood cell. 1.5 is too concentrated because isotonic would be 0.9. So inside would be 0.9%. Out here is 1.5%. That's too concentrated. So water's going to move outside to try and lower that because this number will go down as this number goes up when I reduce the volume inside and increase the volume outside. What process is this? Well, water is leaving the cell, so we call this crenation. What about a 0.7% solution? Now there's too little ions outside. The concentrated solution is inside the cell, so my water is going to move into it to try and get this concentration inside to equal that of the outside. So this would be hemolysis. And then this solution right here, this is close enough to our target number that we can just say, oh, it's isotonic, nothing should happen. Normal biological function is anticipated. All right. Suddenly the class became relevant, right? All this chemistry shit, you're like, I don't need any of this. And then this is the one slide, probably, of all the slides I have for you in the entire class. This is probably the most important one for nurses. So if you have any questions about it, let me know. This is about the extent of the nursing program that I know is relevant to you. Everything else is generally relevant, but the foundation of stuff that you learn later may not be apparent yet. So, all right. There's your homework practice. I believe that is the end of Unit 8. We don't have that much time, so I'm going to just open Chapter 9 real quick, and we'll just talk very briefly about what it is. All right. Oh, there's a cat here. Do you want to say hi? Maya says hi. She says hooray also. All right. So give me just a second. Why isn't this escaping? There we go. Let me load the slides for Unit 9. All right. Oh, there are a lot of slides in Unit 9, so okay. Well, we can do one of these sections here today because we have 7 more minutes left. So we're gonna do the first section here. Probably gonna have to have a class on Wednesday, unfortunately, just to get through the rest of Unit 9. So I can do Unit 10 next week. All right. Chapter 9 is about different types of chemical reactions. There are a lot of slides here, and there are a lot of different topics, but we're going to kind of breeze over several of them. I'm going to show you the easy way to try and interpret a lot of these. So let's do that. So The first part of Chapter 9 is going to be just categorizing different types of reactions here. I must also not be on the right slide here. And so there are 5 different categories that we're going to classify reactions in. And I'm going to show you examples from those today. This will be the last thing we do today. So the 5 reaction types are combination, where I combine things together, decomposition, where I split things into other things, single and double replacement, swap out substances, and then combustion is any reaction with oxygen. So those are the 5 types of reactions with a brief description of them. We're going to show you single and double replacement in detail, so don't worry if you're like, I don't understand what this means. That's totally okay. The other ones are pretty intuitive. Are you combining or splitting it apart? That will tell you if it's combination or decomp. All right, so let's look at these examples here. When I have a combination reaction, I am taking 2 elements and combining them together to create a product. Element A plus element B creates compound AB. Now, these shown on the bottom here are examples of combination reactions that just so happened to need exactly what was shown to combine them. Oops, sorry, I didn't mean to do that. However, if I do something like this, this would also be a combination reaction because I am combining 2 elements, sodium and chlorine. Even though I have multiple sodiums being put in there, the end result is that I combined them together. So whether the coefficients are 1 or more than 1, if the product is a compound of the resulting elements jammed together, it's a combination reaction. The opposite of this would be decomposition. So if I have something and it falls apart, and it is the only reactant in the equation, we have a decomposition. So for example, calcium carbonate can be reduced to calcium oxide and carbon dioxide. So I shouldn't use reduced because that means something different. It decomposes down into calcium oxide and carbon dioxide. Carbonic acid, this reaction is what's going on in my seltzer water right now, which I should have another sip of. Except I've drank all of it, unfortunately. Carbonic acid is the combination of water and CO2. It can also decompose back into water, and then the CO2 bubbles away. Now, what about these replacement reactions? Oh, there's another decomposition one. Replacement reactions require you to swap one element for another in a compound. So if I have something like this, I might swap A and B. And then the result would be this. So this would be a single replacement, because I am replacing one thing in a compound. Now, a double replacement would be something like this, where I do the swap again, but now I have swapped in 2 compounds. So this one's single, and this one's double. And so the result of this would be... Oops, that's not right. The result of this reaction would be that. So if you are looking at a reaction and you swap one element for another, in the products. Then look at the number of compounds you have. If there's only one compound in it and the other thing is the element that was swapped out, you have a single replacement. If you swapped two things to make two different compounds, then you have a double replacement. Oops. So here are some examples of single replacement where I swapped A and B. So here I could do this, so I'm going to swap these two. Here I could swap this. And so it doesn't always have to be the first element. It could be either element. And then for double replacement would be something like this. Oops. So here I'm going to swap A and B. And so we'll do that here. So this and this swap. And you can see that I end up with a different result. And then down here, this and this swap. And I end up with a different result too. And then finally, the last reaction that we have is just combustion. If you react something with oxygen, it's a combustion. The last thing I want to mention, and I'm going to bring this up again later, is that whenever you do a combustion with CH or CH and O in your compound, the results are always carbon dioxide and water. So this is why we burn gasoline and have concerns about CO2. Because burning any hydrocarbon or any carbohydrate, the results are CO2 and water. This is why you exhale CO2. Is because your body combusts things like glucose, which is a carbohydrate, has C's, H's, and O's in it, with oxygen. It transports the oxygen to your mitochondria, combusts the glucose, you get ADP and or turn ADP into ATP or something like that. And then it carts the CO2 back to your lungs where you breathe it out. All right. I believe that is all the time that we have. So when we come back on Tuesday, I'm going to just give you these reactions here. There's the homework practice for that section. I'm going to just have you tell me what these reactions types are. We'll just start there. But that's all I have for today. So I'll put quiz number 8 up later tonight after my other class. Make sure to finish quiz number 7 and lab worksheet number 4. Those are going to be due tomorrow. Those will both close on Wednesday. And hopefully by Tuesday or Wednesday of this week, we'll finish chapter 9. So that quiz will go up later too. Yeah, that's all I got. Have a wonderful rest of your day. Thanks for coming to the lecture. And we'll see you tomorrow. Take care.